Hi everyone, this is John Wen. Today is March 22nd, 2020. I will record this video to briefly talk about IC-PCP algorithms, and this topic will be separated into two videos. And first video will be talking about the detail of the IC-PCP algorithms, and the second video will talk about the Java code implementation of these algorithms. So let's get into the details. This IC-PCP algorithm falls into the category 1 of the scheduling algorithms, which is given a deadline D. It will find the schedule that minimizes the monetary cost while satisfying the deadline D. And the strategy of this algorithm is also very simple but effective. Firstly, it tries to distribute the deadline on each task as a sub-deadlines, and then it will identify the partial critical path, which also called the PCP, and assign the PCP on the cheapest virtual machine that satisfies all task sub-deadline, so that we can make sure every task is meets its deadline, and then the overall workflow meets its deadline as well. Then we will adjust the EST, which stands for the earliest start time, and EFT, which stands for the earliest finish time, and LFT, which stands for the latest finish time for the related tasks. So let's go into the algorithms. Firstly, you can see the input of this algorithm is a graph of the workflow, which has a task and edges, and also we have the deadline constraints D. Firstly, we will determine the available computation services. You can see from this example, we have three types of virtual machine that can be used or leased from the vendor to execute the workflow, and which is a S1, S2, and S3. And we also have the information that how long it will take for every task to execute on different virtual machines. So you can see here for T1, if we are execute on the S1, it will take 2 time units, and it will take 5 time units if we execute on S2, and S3 will take the 8 time units, which means S1 is the fattest virtual machine we can lease from, and maybe it's the most expensive, and S3 is the least fattest one, and maybe it's the cheapest. And we will add a T exit, and we will also add a T exit and T entry to the graph, and the corresponding dependencies to G. So you can see from this graph, we added a dominoes of T entry and add the 0 edge weight to its children, and we also add the T exit and add the edge weight as 0 from all the parents. So here we introduce MET, which stands for the minimum execution time of the task. So initially we'll assign the MET as a node weight. That means we will assign the fattest virtual machine, and with the fattest virtual machine we'll have the shortest execution time or minimum execution time. So you can see I highlighted the first line, and this value will be assigned to each node initially. And for the edge weight, we will assign the transfer time between the nodes and its parents, and after we assign to the PCP, and on a certain type of virtual machine we can adjust as 0 if the task of parents and task of child are assigned to the same virtual machine. So moving forward, we will compute the EST and EFT and LFT for each task in the G. So you can see there are three formulas which calculates EST and EFT and LFT like this. For the EST of entry nodes, it will be signed as 0, and for any nodes between the exit node and entry node, and we will check the maximum EST plus MET plus TT, which stands for transfer time between the parents and this node. And for the and for the EFT, we will use the EST calculate just now to plus its minimum execution time of this task. So these two are calculated from left to right. And for the LFT, we assign the deadline to the TXE node, and we will calculate reversely from right to left in the graph, and to check the minimum LFT minus MET minus TT. So you can see here the earliest LFT is a bottleneck. That's why we choose to check the minimum instead of the maximum, and that means the worst assumption. So afterwards we will, if there's exist, so looking from this algorithm, we can see after we assign EST, EFT, and LFT for each task in the G, and we will assign the AST and AST for exit node and entry node as 0 and D, and then we marked the T entry and T exit as assigned. So these two nodes are assigned because they are dummy nodes, and then we call the assigned parents from the exit node. So this assigned parents is algorithm 2 in this paper. Let's move forward to talk about this algorithm 2. So now we are calling these assigned parents on the exit node. So while the exit node has an assigned unassigned parent, we will do this. We will initialize an empty PCP, and we will assign the exit node to TI. And while there exists an assigned parent of exit node, we will do to add the critical path of this task to the beginning of the PCP. So here we have a definition to introduce, that is critical parents of nodes is an unsigned parent of TI that has the latest data arrival time at the TI. That is, it is a parent TP of TI which has a EFT, which is earliest finish time of parents plus a transfer time between parents and these nodes is maximal. So that means the critical parents is the longest path between these nodes and to the parent nodes, including the transfer time and the parent's execution time. So we will do this recursively to find the critical path. In this example, if we are calling from the exit node, we will find the critical parents. Firstly, we will check the T9 in this graph. The minimum execution time is 5, and T8 is 3, and T7 is 5. Actually, T7 and T9 has the same value, but we will pick up one randomly, so we pick up the 9 in this case. And then we will recursively call assigned parents on the T9. So you can see T9 only have one parent here, so the T6 is assigned as a critical parent, and on the T6 we have two parents, T3 and T2. So you can see here T3 has the execution time of 3, and T2 has execution time of 5. So the transfer time is the same, 2 plus 3 is 5, 2 plus 5 is 7. So apparently this path will be longer than this path. So we will choose this T2 as a critical parent of T6. So you can see here a PCP is constructed from the exit node to the entry node. So let's move forward. After we get the PCP, we will assign the PCP to an existing instance or a new instance. So this is algorithm 3, that is to assign the PCP to a virtual machine for executing. So you can see here if there is any available or existing instance, we will check if it's applicable. The applicable means the task can be scheduled on the instance such that each task of the pass is finished before its latest finish time, and also it will means that the new schedules use a part of the execution time of the instance, which is the remaining time of the last time interval of that instance. So you can see here, if we cannot find any applicable existing instance, we will just launch a new instance with the cheapest service that can finish each task of P before its LFT. So the idea is pretty straightforward, but we will elaborate more during the code implementation, because there are several cases or scenarios when we deal with the existing instance and whether we check it's applicable or not. So this is how we assign a PCP to a virtual machine for execution. After we assign the PCP, we will know which type of service or which type of virtual machine we assign to this PCP, so we can update the actual finish time, actual start time, and LFT for each of these tasks. Also, we will update the EST and EFT for all successor of TI. And we will also update LFT for all predecessor of TI in this critical path, partial critical path. And keep in mind, we also update EST and EFT from left to right, and we update LFT from right to left. So for this example, because they are assigned to the same virtual machine, the transfer time becomes 0 instead of previous. We have previous value here, but now it's become 0. And for the EST, for this one, T2, because one assigned to the S2, this one means the first instance of S2. Because we assign to S2, we can check in this table. S2 has 12 time units, so it will take 12 time units to execute, and then we can update the T5 based on this 12. 12 plus 2 is 14, so that means T5 can start from the 14 time units, and T5 will take 3 time units as minimum execution time at this moment. So we will have 14 plus 3 is 17 as the earliest finish time. And then we can update the T8 based on this T5 as well. T5 is finished at 17, so the T8 can be started at 17 plus 4, that's 21. So you can see here, 21 is updated. So in this graph, if it is updated in this round, there is a star behind the number, follow with the number. So after we get the EST, we can get the EFT for the T8. T8 in this table takes 3 time units to execute, so 21 plus 3 is 24. So you can see we successfully update all the successors of these critical path tasks. But now we are going to update the LFT of the parents or predecessors of all tasks. So you can see here only T3 is a predecessor of the T6. So T6 we can get from the T2 is 12, and we can get the execution EST, I believe is 12 as well, because it will takes 8 to complete. The EFT also update to 20, and now we are looking at LFT. So we are basically looking at the EST of the T6 is 12. 12 minus 2, I think should be here. I think here is a typo. Here should be the 10 instead of 12 because we have to consider the transfer time as well if you're looking at the formula here. So you can see we need to subtract the transfer time as well. So I believe here is a typo. Here should be 10 instead of 12. Okay, so let's moving forward. And after we update all the successor and predecessor of the task on this critical path, we will recursively call the assigned parents. So now you can see the parents of this all the tasks in this critical path is only T3, which is a T6 parent. So we will call the assigned parents on these nodes. So basically, we'll do this again. And based on this one, start from this one, we will check all the critical parents and then assign to the PCP because it has only one node. So basically, this will become a new PCP. And then we will assign it to either the existing instance of virtual machine or the new instance of virtual machine, as we talked about previously. And then we will recursively update its parents or the child, EST, EFT, and LFT. Because you can see here, no parents or no child will be needed to update. So here we only have the T3. In this case, we assign this T3 to S3. So that means we will update the EFT. You can see here T3, if we assign to the S3, it's 9. So the EFT of T3 updated to 9 in this case. So moving forward, because we have done this pass, remember this line is we called on the exit node. While exit node has assigned parents, we will recursively call. So T9 is done, then we will go to the T8. So same way, we will find the critical path. In this way, we will find the T8 and T5 as a critical path. And from the critical path of T8, assign it to the S2. And we will also update the EFT, EST of the successors and the LFT for the predecessors. So in this case, we don't have the child for any of tasks in this critical path, but we have the parents, which is T4 as a parent of T8, that we need to update the LFT, and we also need to update the LFT for T1. So you can see from this round, we have T8 updated, and T5, because it has star here, T5 updated, and T4 updated, and T1 updated. So T4 updated with the LFT, T1 updated with LFT as well. So moving forward, we will do the call assign parents of this critical path. So we only have these parents, T4, as parents of T8. So we call assign parents on T4. It will recursively find the critical parent and then form another PCP. And then we will do the assign a path of this PCP again. You can see here we assign this to the type 3 virtual machine instance 2, and that means we will update the LFT, EST of this and LFT for these tasks with this S3 type virtual machine. So you can see here we get update on the T1 and T4 because they have stars, and the T7 because we need to update its successors on EST and EFT because we have no parents of those tasks in this critical path, so we don't need to adjust the LFT but only the the successors EST and LFT. So you can see here T7 has the EST and the EFT adjusted. So finally, we will look at the T7 after all have been done. T7 will be last parents of this TXE node, and we will check, because it's a single task, we will check whether it will be assigned to existing virtual machine instance or a new instance of virtual machine. And luckily, we can find a time slot available on S3 instance 2. So that means we will reuse the existing instance. So you can see here T7 will be updated on the last round. All the others will have no starts. Only this one will be updated. So until now, I think we have assigned every task or every critical path to the virtual machine that meets the deadline constraints or some deadline constraints of every task. So overall, the workflow deadline will be met. So I think it's briefly the idea of how the IC-PCP works. So if you want to look into more about the algorithm, you can definitely refer back to the paper and try to comprehend more or in depth. So let's have a summary of this IC-PCP algorithm. So firstly is distribute the deadline as a sub-deadline on each task, and then it identify the partial critical path, which also called PCP of workflows, and assign each PCP to the cheapest virtual machine, which satisfy the sub-deadlines, and then recursively adjust the EST, EFT, LFT for the tasks on this PCP, and then adjust the EST and EFT for the descendants of PCP, and adjust the LFT for the ancestor of the PCP. So it apply this step 2 to step 6 to the exit node recursively until all the PCPs are assigned. Then the plan is done and will be assigned to the workflow executor. So I think this is pretty much about the algorithms. Hope you enjoyed this video. I will continue the Java coding implementation in the second video. Hope you will enjoy. Thank you so much. Have a great day.